Good morning to one and all present over here. We have our speaker, Dr. Manjunath from Manipal Institute of Technology. He'll be taking over the session on acoustic event detection. Manjunath, sir?
Yes, madam.
Yeah, you
Yeah,
can take.
yeah. Good morning, everyone. So, in the last two sessions, in the first sessions, we were discussing about the intuition of deep learning approaches. And in the second session, we were discussing about the machine listening. And in the machine listening also, there are two important problems we discussed. One is acoustic event classification. Another one is the acoustic scene classification, acoustic event detection and scene classification. So now I'll try to we'll try to build some models, some audio recognition based models. And then also, if time permits, we will discuss about the necessary pre-processing conditions. How can we use the pandas for pre-processing? That if time permits, that we will discuss. And before that, we'll try to build one acoustic event classification, or we can even take the same classification as well. Both here it is to be in event classification. I will predict the individual events present in any one of the scene. Like in the home scene, I will consider, and then I will distinguish the number of events in that. In the same way, in case of acoustic scenes comes, then park, residential area, and all those things we will identify, recognize. So I will try to discuss with one of that problem. I will try to write one code from the scratch. Hope you received the data set I already shared with you. So hope you received the data set, that is kitchen data set. There are two acoustic events are present in that kitchen environment. One is the flatware sorting and another one is the water tap running. So we will use those two uh, sounds and try to build one model, simple first one as the logistic regression. Let us say that model only we will try to build, and what are all the important things to be consider and how to pre-process the audio data, how to read the audio data. If it is the similar situation in case of whether if you are working with text as well as the image, I will collect I will store the data, I will segregate the data into different folders, and each folder I will name it as the class name. For example, if I am developing a sentiment classification model, then I will create a folder positive sentiment, then I will store all the text files in the positive sentiments, and then I will store all the negative comments in the negative posts in the negative folder, and then neutral comments, neutral text in the neutral folder. Likewise, here also I will divide, segregated the data set is well-known data set. So already segregated the data. So flatware sorting is present in the flatware folder, and then water tap running are present in the water tap running folder. So how to read that data, how to represent that data, how to analyze that data, that we try to do it. So it is good if even if you are trying to execute and trying to write code with me, so then it will be a nice. So even you if we get any errors or anything, so we will try to resolve ourselves. So from basically from scratch, try to write the code and try to build a model for those data set which I already shared. That is zip file. Let it be zip file itself. So I'll try to read that from the data set. Please, now I will write a code in the Google Colab. So we can use our Colab, and then you can log in with your Gmail account. So we'll start using the Google Colab. And if you do not understand at any point, at any steps, just to discuss with me, just stop me and discuss with me. So from my Chrome. So I already opened the Colab, Google Colab. Hope you will also open it. So just type Google Colab and then open the Colab framework. Just I will rename this. Yeah, acoustic event. So before starting, before, sorry, I will share the screens. I did not share the screen. So hope my screen is visible. Yeah, now just you. Is it? Yeah, I think it's visible. Yeah, just open the Google Colab and just I renamed this acoustic event.ipynb. I have not done anything yet. Yes, now please, if madam already shared the data set, so you download that zip file and keep it in your download folder wherever you want. Zip file. Yes. So yeah, hope you downloaded. Yeah. Just for the first step is I'll just load that data set into my Google Colab environment. Different methods are there to store the data directly to the Google Colab. I think other speakers also might explain this. One method is you can store all the data into your drive itself and read the direct mount the drive and then read the directly from the Google Drive itself. Other method is like you can directly upload as a file and use that file. So I will use the second method. I will upload as a file, that zip file, and then I will use the data set to develop a model for the audio recognition. So for that, Google Colab provides a file upload option. So just I can import that option from the Google Colab from Google. Yes, so files is imported. So hope you are also working with me. So I will take a variable uploaded is equal to files dot upload. Right, then from the Google Colab there is files, and from the files I try to upload my data set. We just run on in this by typing the shift enter. Then it will ask me to choose the files. So I already downloaded the zip file data set and kept it in the download folder. So I will just traverse over there. So it is in the downloads. So you can go through whichever folder you kept that one. So I think name of the data set is kitchen 2 and some numbers followed by 001 zip file. Just uploaded the zip file. Data set already shared, and then I'm working with the Google Colab. One advantage of using the Google Colab is no need to explicitly install the n number of packages required to execute all the steps in the Python. Already the Colab associated with all the most of the packages, so no need to explicitly install them. So 33%, it just take few seconds. Anyhow, only 2 classes are added because of this time constraint. Yeah, a few minutes, and also for you also it may taking time to upload. Yeah, it's 100% done. Yes, you can see all the uploaded files to your Google Colab environment here in this left side bar. Here we have a folder symbol. If you just take a mouse over there, then it will highlight the files. Just click on that and see here. I already stored the zip file here. The zip file is present here. So I will unzip it just by using the command unzip. So all the Unix commands you can execute here by using this explanatory mark unzip. And then folder name kitchen 2. Just you type just 2-3 characters, so it will show the complete data set name. So unzip, just I loaded the zip file. Now I am trying to unzip it. So shift enter, I'm executing it. Yeah, so it's unzipped all the content here, and then even we can just refresh here the file content. Yeah, if you are lagging behind or if you want me to stop, you can tell me at any time. And here refresh button is there. Just I will click on the refresh. You can see here kitchen 2. So just unzipped it, and here we have the unzipped folder kitchen 2. In the kitchen 2 also you can expand it. I can see that there are 2 folders. One is flatware sorting and another one is the water tap running. And even expand the water tap flatware sorting. These are all the n number of audio signals are present. Their extension is the .wav file. And also similarly in case of water tap running, the data is present, audio data is present. So I have all my data in my execution environment. Yes, now we will try to read this data. There is a master folder kitchen 2, and within that there are two subfolders, flatware sorting and water tap running, and each folder we have the different audios. Even if you are working with the, as I told in the beginning itself, even if you are working with the image or the text, again it is to be the same. I will segregate all the files into different subfolders and yeah, different subfolders. It is necessary to read the data into the execution environment. Yes. Yeah, now this is the path of the data. I want to take the path of this data kitchen to where exactly present. You can click on these 3 dots, copy the path. So I can take the path, just click on these three buttons and it will show the copy the path. So that path I will use it as a separate folder, audio folder. Just in few seconds we'll try to execute it. Yeah, this is the path. /content/kitchen2. Yes, this is the path. You can execute any of the Linux commands as well just by typing the audio folder, explanatory mark. Then we have here complete the audio folder kitchen2. Just I want to try to read a signal, one signal from the audio signal from each of the subfolders present in flatware sorting and the water tap running. So for that, if you read, write for feature extraction, anything, the Python provides the popular package that is also known as the Librosa. So just I will import the Librosa. Librosa helps me to read the data and extract the features from the data, right? And just you need to give the path for to the Librosa functions, so it will automatically read the data. So I will use the Librosa is imported. Now I want to read the data. So I will write two output parameters and then librosa.load is a function, helps me to read the data from the flatware sorting. In the flatware sorting, one dot wave is there, one minus one dot one hyphen one dot wave is there. So I want to read this into my execution environment. It might be MP3 as well, whatever it is. Just I will want to load here, Librosa load. Librosa load read the function and returns two output arguments. One is X, another one is the FS. So I will discuss those, what are X and the FS in case of if you are working with the signal processing. So here I have a librosa.load. Just I want to give the path. Already I have the main folder path, that is audio folder. But this is not enough. Within the audio folder, I have to go to the flatware sorting, and within the flatware sorting, I have to go to the -1 dot wave. So still I need to write the path. Even we can write it as manually, like /content/kitchen2/ flatware sorting /1 dot wave. In that way also you can write, because already I store it into one folder. So just I do not want to I want to use this folder only, audio folder, followed by another folder, which one, this is a kitchen2, followed by that I want to require the flatware sorting. So flatware sorting. So it is present within the flatware sorting. I want to read the wave file 1 minus 1 hyphen 1 dot wave. All are these strings. So I'll just represent them as in the double quotes. Yeah, but these are all together like folders followed by /flatware sorting followed by 1 minus 1 dot wave should be. There are two ways to handle. There are separate fold combined together to make one path, complete path. You can use the join function. Otherwise, what you can do is you can use plus symbol to connect all these three strings together. So I will use the join function. Up to you, anything you can use. Import OS, that is present in the OS function. Librosa.load. Here what I will do is I want to combine all these function. OS dot path dot join So join all these folders together. Audio folder, flat phase sorting. I'll just close the parenthesis. This is fine now. So XFS Librosa load audio folder flat phase sorting 1 minus 1 dot wave. Yes, complete. This is the just I will give the path to the Librosa dot load. So it finally reads the data and returns the X and Fs. Yes. Now, what are exactly the X and what exactly the Fs? X contains the samples. In case if you consider the image, then in the image we will consider the basic fundamentals, how the image is constructed based on the group of pixels. Right, the pixel we consider, but in case of if you are working with speech processing, or if you are working with the any wave signal processing, or the one-dimensional signal processing, or the speech signal processing, audio signal processing, in this situation the signal is formed by the samples. We will call them as the samples. So you can visualize those samples, right? These are all the samples. Where there is a high value, then there is a energy, there is a sound in that represent the positive value, more positive value. And where there is energy, yeah, that represent this all samples together represents the sounds, right? So we can try to plot this sound and we can see how exactly it looks. And also Fs indicates that the sampling rate, how many samples are present per second. There are 22,050 samples are present in per second. So X is have the symbols, and you can see that how many seconds audio signal it is, X by Fs. Sorry, length of length in MATLAB, I think len is in case of the Python. Yeah, it is approximately 1-2 seconds of so audio signals are present. So total number of samples here we have 44,251, and then divided by Fs. So that is in case of there are per second there are 22,050 samples are there. So total length of the signal itself is the approximately 2 seconds. Yeah, now I have the complete signal now, audio signal now. So using this audio signal, try to plot that sample signal and check that how this signal look like. So to plot that, I can use the matplotlib. So from matplotlib, just it is not a good method to use. Usually all the packages are imported initially at the beginning itself, but wherever the packages required, whatever I'm there only I'm using it. So from matplotlib, so I want to import the pyplot function. We use it as just plt. I do not want to write every time pyplot. So yeah, that's all. Once if you have this, sorry, plt. So plt dot show, or it is plt dot plot. Sorry. So using the plt dot plot, x is the samples, right? So this is the audio signal. You can see here there is a sound is here. At this point we have the in the x-axis we have the number of samples, right? So 44,000 something are there. X-axis is the number of samples and y-axis represents the amplitude in decibel, strength of the signal. So where there is a highest strength, there is a signal, right? Here it is to be there is a sound is there, flat wave sound, and here some silence is there. After that, just a small audible sound, after that silence, and then here it is a clearly audible sounds are there. Right. So I think we can listen that sound and then it is better understand this, right? So for listening the sound, I can use IPython, interactive IPython shell. So that is also for listening from IPython. Display, there is a packages there to read the sound. So thanks to the Python providing all the packages, just we need to organize them properly to get our to implement the task. So audio, using this audio I try to play the sound audio. Then it takes two parameters, one is samples and sampling rate. So first argument is the data. It will take the samples. X, it is written by the librosa load, and then rate is the sampling rate. I stored it in the fs. So we can see now. Yes, initially, and at the end there is a strength of the signal is high. Initially started with the little audible sound, but when at it ends, then is the strength of the signal is to be high. So the same thing, the same samples are also representing the same thing. Yes, you can visualize any of the data like this way. So we can take the water tap running as well, and then anything, right? So that I stored the signal and then I'm trying to analyze those signals. Yes, so this is the one method and this is the one way to analyze the signal. Now what I have to do is I want to build the one classification algorithm. So what it has to do is it identifies the, if I give the any input signal, it should identify that whether the signal belongs to a flatware sorting or it is a water tap running. It's a pure classification problem, supervised classification problem. If I give the input audio signal like this is the input audio signal. If I give, then it should be able to attach the tag to it. That tag represents a class, whether it is a flatware sorting or whether it is a water tap running. So for that, if you want to build a classification model, a traditional all classification model first includes two stages. One is feature extraction stage. Another one is the as usual, that is a classification stage, model learning stage. But yeah, now also what from this audio signal, I want to extract the features. So I want to extract the different features from this. So might be a zero crossing features. Zero crossing is this nothing but how many times the signal crosses this zero line, zeroth axis, or this, yeah, this axis, that is the zero crossing. And then the energy of the signal, the what exactly the energy of the signal at the particular time points, that is time periods, that is one of the signal. That is those signals are directly taken from these samples itself. Those are the two important features. But most of the people, what they will do is rather than directly taking this features from directly from the samples, those samples are also called as the temporal features. Time feature, this is the time I'm representing over the time, directly taking from the samples itself. Those are also known as the temporal feature. They first convert this signal into a frequency domain, from time domain signal to a frequency domain using the Fourier transform. one, frequency Fourier transform FFT. So apply the FFT over it, and then once we apply the FFT over there, then again we can extract the different other type of features like spectral features. Those are also known as the spectral features, spectral flux, the different types of features, spectral feature, frequency features also we can say. We can take the temporal features directly from the time signal, or you can just apply the FFT over, then we'll get all the frequencies. For each time sample, there is a corresponding frequency we will get. So based on that, even we can extract the features. That is the two methods. So, but most popular methods in the speech processing are the MFCC features, that is mel frequency substral coefficient features, right? So those are MFCCs represent the human auditory systems, and then the human auditory system, the MFCC features are the earlier days, those were the state of the art features. Those gives the highest recognition accuracy and extract the features from the lower frequency components. Yeah, I will not go much in detail to that. Just I will tell that how to extract these features. So first I will try to extract the MFCC features from each of the audio signal. So for the MFCC features, it is not like if this is a one signal. If I tell you to extract the strength of the signal or this energy of the signal, and if you take all this sum of this signal, yeah, this is completely a sum of the signal. I will take the sum of the signal and then I will try to evaluate the energy out of it. But that is not the case. If you take entire signal, then each time I will get only one feature value. That is not enough to represent the entire features present in the in this complete audio signal. That is why the audio signal is divided into divided into a number of windows. So here I have the representation. Just I will show before that. Everything that is do by Librosa itself. Just I want to explain little theory behind that, how to extract the features from the signal. So now I have a complete signal here. So samples, I have samples 0.2, 0.3, whatever it is, samples are there. If you draw this sample where there is a signal, then there is a sounds will be presented. And then now I have to extract the features out of it. If you want to extract the features out of it, then we have to divide this entire signal. This is 2-second signal, and I have to, and it contains approximately 44,000 samples. Right, so 44,000 values are there, and per second some 22,000 values are there. So what I will do is I will divide this entire signal into fixed length window. Let us say, for example, it is 200 samples, right? 200 samples in window. I have the 200 samples here. I took the 200 samples, and then next to 200 samples. Next to 200 samples will take by using this overlapping window. The overlapping, how much overlapping is 100. I'll consider is the 100 overlapping. Window length is 200 samples, and then overlap is 100 samples. Yes, so it helps me to extract. I will extract some features out of this 200 window, and then again I will move that window to 100 places forward, and then again extract the features. So 100 values, they are the overlapped values. Again here 100 I will take, right? So in this way. So each of them is also called as this window. Each of the window is also called as the time frame. That is also called as the window, that is also called as the frame, that is a time frame. So every time frame I will extract the features. So if you may extract the mean of the value. So every time frame we will get the mean. Then how many frames are possible in one audio signal? How many frames we will get? So usually how many frames we will get? Suppose how many time frames will be there. So suppose if I have the length of the signal is 12. So 12 samples are present. Let us consider an example. 12 samples, and then the window length is, so otherwise I will take a one simple example. 6 are there. 6 samples are there. So 1, 2, 3, 4, 5, 6. And then I will take a window length. So first window length as 2, right? And then followed by the steps length. Step length I will take the 1. So I will deriving the formula to count the number of time frames. So this is the overlapping length or step length, and this is also called as the window length or the frame length. This is nothing but the number of samples plus 1. So we have here 6 plus 2, right? So 6 plus 2 is nothing but 8 plus 1. 9 frames are possible here, right? Yeah, you can check that. So total 9 frames will be there. So in this method we can extract the feature out of 9 frames. I can extract the whatever features I want. So you can extract the mean of this. For the if you calculate the mean of one time frame, so then we will get the mean of one time. Only one value we will get. Mean of all the values, average of all the values in a time frame. Every time frame, if I have a 6 time frames, then I will get the 6 values. Those 6 values I can consider it as the features. So yeah, this is the one method. Whenever we are working with the signal processing, just we need to remember this. And the same method even we can use in the convolutional operation. Whenever you are using the convolutional neural network, and we can consider this window as a filter, and this you consider it as the signal as well as the image. If you consider this image, then the filter is of size 2 into 2 dimensional it is. Or if you are considering it as the audio signal, then you can consider the filter size as 1 into 2. So it has the some weight variables, and take the dot product matrix multiplication between the pixel values and the weight parameters present in the your filters. Same thing here. Same thing I am doing. Yes. So, but whatever I explained the theoretical point of now, that is even just I will use the Librosa. But in the Librosa, all the features are there. So you just need to give the window length and overlap size. If you don't give, then the default window length and overlap size it will take, and it will evaluate the features for us. So I will try to extract those MFCC features, popular features. So, but if you want to extract those MFCC features, then what we have to do? So I have to do is just I have to go to each folder. From first I have to go to the kitchen 2, and within the kitchen 2 I have to go to the flatware sorting. From the flatware sorting, then I have to go to the each of the audio file. First audio file, divide that audio file into windows, overlapped windows, and extract the features. Then go to the second audio file, divide that into a overlapped windows and extract the feature. Then go for this. Once you complete the feature extraction from the flatware sorting, then you start going towards the water tap running. So extract the feature from first audio signal, then move towards the next one likewise. So same thing. Yes. So same thing I am doing. Even in if you are working with the image processing or anything, you have to extract the features from one audio file or one image file or from one text file. So how to read those data from one file to another file folder wise, right? Using the using this Python. Yeah, easiest method is there. I already told that here only one file I have read from a librosa.load, but I have to automatically read all the files rather than manually reading. Automatically read all the files. and then do some for necessary action. This is means the same code is also if you want to rename all the files at one stretch. So read one file after the other file and then rename them. So same method even we can use here. So for that, I will use the list directory function. List directory function. It's not, I will not use from the POSIX list directory. I will directly use it from the OS list directory function. So you just if you give the folder name to here, then it will list the content of that. So I already mentioned the folder name audio folder kitchen 2, right? Folder name kitchen. We can, sorry, it is not kitchen 2, it's audio folder names. Name of the folder, I will just audio folder. Yeah, it is listing flatware sorting and water tap running. If you just give the folder name for the list directory present with the OS package, and it will give all the data present in. So I will use the same for loop I will use. So for the over the OS list directory, then open this folder first and then read all the data from this. So if I will use the two for loop, one with the OS list directory, one is to read the flatware sorting. Once you read the flatware sorting, then again I want to read the content present within the flatware sorting. That is nothing but the data files, right? So for that I have the I will take one for I in OS list directory. So all we know that. So even if you print the I and you can check that. So flatware sorting and then followed by the what is that? Water tap running. The now what I will do is, so from the flatware sorting from the I, that is first I0 index 0 in present flatware sorting, then second one is water tap running. So from the first folder again I will read all the audio files present in this. So for audio file name, audio I can take again from each directory present in this I os dot list directory I. So traversing over the folder within the folder. But is this audio path is right? So I only gives the flatware sorting. So I require the complete path. So kitchen 2 within that flatware sorting, and then within that I have to go to the specific audio files within it. Kitchen 2, then followed by the flatware sorting. Sorry. This side flatware sorting, and then I have to go for the audio file, but I gives the only flatware saying I require the complete path. Audio folder can represent still this audio kitchen 2. So I will take one more complete folder name. So for that what I will do is folder. So any doubts if you are getting, you just ask me. OS path join I will use, again I use the same thing. So till this point I have a folder name, that is audio folder kitchen 2. Audio folder kitchen 2, and then followed by I represent the flatware starting kitchen 2, within that I. Yes, this is the complete folder. So in within the flatware sorting, this is the complete path. I will just pass it to the folder second one. You can just print and check this. Print. Yeah, you can see the, sorry, it's not audio folder, audio file name, right? Okay, that's all. Yes. So I now require just writing the two for loops with the OS list directory. I will use the properly for loop, outer for loop to read the folders, inner for loop reads the files within the folder. So I am reading all the files present in each of the folders one after the other. That's all I'm doing. So 10.3.wave, 11.3.wave, I'm reading the file. Once you are reading the file is nothing but, now what you will do, you can just um, yeah, extract the features directly from each of the file. Yes, so how can I extract the features from each of the file? So let it be. So extract the features, first read that file by using xfs librosa.load. I already told one of the simple example how to use the librosa.load. Similarly, here one file after the other, I am using the librosa to read the data. I am using the librosa.load. So librosa.load, it takes the 10 minus this audio file name, again produces the only this file name 10 minus 3.wave, but I require the complete file name. So if you require the complete file name, then again I have to use the what I have to use, I have to use the OS path. So audio file I can take, so just I require OS path join. I just path join, I'm making use of the complete path. So I'm getting these, the paths are the only half of paths are present in different folders. So first path is the audio folder, right? It comes till kitchen and then followed by the I, right? Audio folder. I gives us the audio folder, and audio folder, after the audio folder I gives the specific folder name, flatware sorting or not. Once you get the flatware sorting, then we will get this a specific audio file name. Yes, that's all. So this is the audio file. Give that to librosa.load. So that's all. So it reads the data and returns the XFS. So just I check this. Yeah, the reading successfully. So all the audio files I'm reading, and it gives the X and FS value. And from the X value, I can try to extract the features directly. So which method? I can try to extract the MFCC features from the directly from the Librosa. So MFCC is equal to Librosa. So many packages are available to extract the feature in as well computer vision as well as in the audio signal and speech processing. Because nowadays the concentration is not more on the feature side, it is always on the model side. We are using the deep learning models, and always we use the MEL spectrogram features or MFCC features. We directly extract it from the package and use as it is. Try to build new models for that. Librosa.features, within that we have the MFCC. Yeah, just to pass the, I will use the default window length and the frame size. Yes, we can see MFCC. You can see the MFCC. MFCC takes that. Y is the samples. SR is the sampling rate, right? And then number of MFCC features, we can extract as many as MFCC features. Default count is 20, and then followed by the Yeah, default count is the 20, and then it will take the default window length and the default overlapping length to extract the features. So now read the X values using the LibreSA load, and then I'm just extracting the features by using this X and FS. So that's fine. So just I can check, print the shape of this MFCC extracted from each of the audio file. MFCC dot shape. So that shape is much required because I want to store all these into a single array to make it as a matrix. So matrix requires the same dimensions. So look into this. So 1.1 wave, it is read and it's extracted the MFCC features, 20 MFCC features from the 87 time frames. Right, so here the audio length are not fixed. Some of exactly 2 seconds, some of them as the 2.5 seconds, some of them 2.3 seconds. So because of that, we will get the variable number of the time frame. Time frame is nothing but window length, 2-second window length. 2 millisecond window length or 200 samples window length I will use, and then divide the signals. And from each time frame, I will extract the features. Here I am extracting 20 features out of 87 frames. So this audio signal 11.wave is of same length, so that is why it gives the only 87 time frames, and 6.2 also gives the 87. But you can look into the 7.2.wave. There are this audio signal is length of the third audio signal is greater as compared to the first and the second one. So in such situation, we will get the 88 frames. So I can't load all this into a what is that single matrix like that. Here I have one example. So one is 2086 and another one is the 2087. So I can't, one has the 86 length, another one has the 87 length. I already create a matrix of columns contains the 20 and rows contain the 86, but suddenly if 87 comes, then I can't possible to append it to the same thing. And one more major constraint of the learning algorithms, mainly machine learning algorithm, they require one-dimensional feature vector. Only one-dimensional feature vector of size anything. So it is one-dimensional feature vector and followed by the one label for training. So this is the feature vector and followed by the label is 0. 0 may represent the flatware sorting. So I require exactly a one-dimensional feature vector. But when you extract the feature from each of the time frame, then from each time frame you will get the 20 features. Right, and second time frame you will get again 20 features. So these are, in the first case there are like this 86 time frames are there, and each time frame is of length is of 20. Right, I have to somehow convert this into a one-dimensional array. Right, because it is the number of because I require only one-dimensional feature vector. Here it is not one-dimensional feature vector, it is a two-dimensional matrix. So I want to convert this into a one-dimensional feature vector. So that is a constraint. So we have to prepare in that way. The data set we have to prepare in that way only. Right, even in case of convolutional neural network, I am applying everywhere filter in the 2D matrix. Finally, before going to the fully connected layer, I will flatten into a single dimensional. Same thing here also, I require only one dimensional. There are many methods are there to convert a feature into one dimensional. Some of them are take the mean over the columns, mean of that, and some of them are to be take the standard deviation. Right, mean as well, and some of them are preparing the standard deviation. Some of them are the other methods are also used, bag of words method. right? So bag of words method, we can replace this with the nearest cluster. That is all. There are many methods are there. I will take the simple method. I will try to take the mean over the columns. Because if I take this side again, I will get one feature length is of size 86 because I will take the mean over here. So this is, I will produce the only one value. So then again one feature vector will be 87. So then variable length feature vector I will produce us. So that should not be there. So that is why I will take the mean over this side over all the first value of all the time frames. So finally I will get the one value, and then first second mean over the second all the values. So I will get the second value, then mean over the third row, then I will get the one value. Finally you will get the one dimensional vector of length 1 into 20. So that is what in second feature as well, second one as well, we will get the feature vector of length 120. So I have the only one dimensional vector, and that is also fixed length. So first one is one length of 20 and second one is also a length of 20. So using this I can make a matrix. Yeah, these are all the few mathematical background behind with every features. So it is important as well. So same thing, here I have the produces the different lengths. So I will try to take the mean. So we can take the mean MFCC. So before producing this, I'll take MFCC is equal to mean present in the NumPy. So I think import NumPy as right NumPy dot mean. So I have the mean value now, NumPy dot mean. So try to take the average, mean average over this MFCC. I want to take the mean row wise. X is equal to 1. That's all. Row wise. Now we can check the print MFCC sheet. Yeah, everything is 20 comma 1, that is one dimensional. Everything now we have a 20, so one dimensional feature vector, and each has the feature vector has the 20 values, right? So I can use this for the classification as well, but for every feature I require corresponding label as well. So how to produce that label? So, and first of all, I will store all these features 20 20 20 is producing into n dimensional array. So once you have the dimensional array, that is also called as the feature matrix. So I will create the feature matrix and also as the label vector. Then how can we create a feature matrix? So I will take a matrix features is equal to none. Yeah, features is equal to none. So initialize with the none. Nothing is there in the features matrix. Now I will try to use that matrix to store the results. So I'll comment this. So feature matrix, first I will store one value, and then again once you store the value, then I can keep on appending the values column wise. First I will check whether it is features is none or not. If features is none, yes, exactly, initially it is none only, then directly I will store this first extracted MFCCs to the features. And also it is better, I will store the corresponding label. Label is nothing but folder name, that is flatware sorting, or nothing but the another one is the water tap running, that is available from This is audio folder, kitchen folder. Within the kitchen folder, OS list directory I'm using, it lists the flatware sorting as well as the next one is flatware sorting and water tap running. So I will just store that it into a label. One more, that is a label vector. I will do it. I'll consider it as a label vector. So else it is not within if, it is outside the if. Yes. So if it is not null, already it has the one value, then keep on stack those values column wise, vertical wise. So for that I can use numpy v stack, vertical stack. And then what I will do, already I store the features initially in this features, and then new MFCC comes. So I will store features. Already MFCC is there. First MFCC is stored initially, and then MFCC vertically I will store it into a matrix to make a feature matrix here. That is a feature matrix. Yeah, similarly we can make a label vector. So it is of dimension 1. So label, and then again I can make it as a vertical stack. So label followed by label is initially I store one value, then again keep on uploading the values in that stack. Yeah, that's all. We can print the features shape, right? So I want the finally all the extracted features, extracted 20 dimensional features from all the audio signals, and print label shape as well. So it is reading, and from here, yeah, finally I got this. So just I'm printing at the last. So 40 audio files are there. So 20 from water tap running, 20 from the flatware sorting. So from each audio file, there is 20 features are extracted. So 40 into 20 feature matrix is ready. And then label matrix 40 into 1. There are 40 audio files, and then one is nothing but which audio file it belongs to flatware sorting or whether it is belongs to the water tap running. So here I have, this is complete data. So first 20 are belongs to a flatware sorting, those are the labels, and second 20s are belongs to the water tap running, those are already stored it into a label. And then feature matrix is ready, and then labels are ready. Fine. So then that's all. So in this way, if you are working with anything, then the ultimate first goal is to identify that the feature matrix, and then forming the feature label vectors. One both we will get in case of at least supervised learning problem. In unsupervised learning problem, this labels are not there, but we can construct our own feature matrix for again training the models. Yes. So this is the case. I have the feature matrix, and then I have the labels. And just before giving this feature matrix and divide them into a training and testing, train test split, before dividing into training and testing data, first it is better to standardize the data. So feature map, we can see features. Yeah, this is the matrix. These are all the different features I am already extracted from this, right? So I will try to standardize this data. So standardization is very much essential, because if I have the features I extracted, some of the features are have the high magnitude values. Some of the features are high magnitude values like 50, 30, 40. Some of them are the low magnitude values like -5, 0, 1, 2. Then machine learning algorithm bias towards the high magnitude values and it neglects the low magnitude values. Low magnitude values also may contribute as one of important features. So in that situation, what I will do, I'll scale all the features to a scale, bring them to a same scale using different types of standardization methods. There are two standardization methods, so popular standardization method. One is the zero mean standard deviation. Another one is the min max scaling. Zero mean standard deviation is nothing but we have to subtract the mean from individual features and then divided by the standard deviation, right? That is one method. So we will have one negative range to positive range values like -2 to 2, -4 to 4, like that value we will get. That is the scale. In case of min max scaling, so min max scaling, subtract the mean and then divided by the range. So in that situation, what we will get the values between 0 and 1. Whatever is the methods you can use. So better I will use the zero mean and unit variance. So for that, also called as the standard scalar, and that is already present in the scalar pre-processing method. Directly take it, scalar dot pre-processing. Import the standard scalar. Yes. So I will use the standard scalar, and also these labels we consider. We will standardize this data, and also we consider here the labels. Labels are is in the textual form, categorical values. So finally machine understand only the numbers. So I have to convert these values into the numbers. So for that I can use the one hot encoding method, or we can use the label encoder method. So they are present in the, so I will use the label encoder. That's all. These two methods are required from the pre-processing. So once you get this, then try just directly, I will apply features contains the all the feature. This is a feature matrix. So I want to standardize this data. So just use the standard scalar function. Standard scalar function. So there is a fit transfer within that. Fit transfer function takes the arguments as the features. That's all to standardize the data. Once you standardize the data and then keep them into a separate variable, I will take it as processed features. Yes, same thing. Yeah, processed features. We'll all standardize the data. Right, I'll bring them into all the same scale and as well produces the same shape, that is 14 to 20. Right, so this is one of the method, and then once I scale the values, scale all the feature, next is encoding the labels. Label, I will take the label encoder. Get the label encoder, again I can use the fit functions. So fit the label, so same thing here, also fit transfer features. Here we use the fit to the label. All the labels are stored into a label one. So label fit, once you fit it, then I can use this label encoded values, store it into here. So this is daily dot fit transform. Label transform itself, and we can see label encoding values. Yeah, finally here we have all the zeros. Flat weight sorting are converted into zeros, and then I converted the other values as the 1. Feature matrix is ready, even it is completely pre-processed, and then label vector encoding is also ready. Once both are ready, we will divide the data set into a training set, testing set, and the validation set. Validation set anyhow not required here, just I will use it for the training and then the testing set. So for that we require train test split function. So that is available from the model selection, I think. Yes, scale. So just we know that how are the models are to be, what are all the models can be used, what are all the functions can be used. Model selection. From a scalar dot model selection import train test split. No need to write any explicit code for that. Sorry, it is a scalar. Yes, I have now the train test split data. So to function, just we will use it. And if you train test split, then it will create features for training, that is X. X indicates that the features I will use for the training, and then features for the test, and the labels for the train, and then labels for the test. That's all. X train, X test, and Y train, and then followed by the Y test. So again, same function I have here, train test split. And train test split take the arguments. Those are the processed features I already used. PROC features, right? Yes, followed by the converted labels. Label encoding. So how much test size I want? I just want the 20% test size, and remaining I will keep it as the training. So 0.2. Test size is 0.2. Yeah, this is enough, I think. Yeah. So this is done. Now I use the train test split model. I have now training features as well as the testing features. Once you have all the training and then the testing features, then you can develop our own model. So just I can use here the logistic regression model itself, whatever we discussed, and it is good in extracting the features and good for the low data. We have very little data, and even we can explore this model for the any other sophisticated models as well. Just we need to increase the data set, and then we can change the model. So linear, from the linear model we can just import the logistic regression. That's all. Once we have the logistic regression, fine. So classifier, I have the logistic regression. I think from this everything you know. So to train the model, we use the clf.fit. I think you know this point. And then for training, we have to give the train features. That's also we know. And then why train labels. So model trained. Then I can use for the check further its performance using the prediction. So I will get the predicted labels by prediction is equal to. So just I will use the already trained model clf dot predict. So what I want just to give the test features without using test labels. So but it will predict the labels for us. So once we have the actual labels in the y test and the predictable labels in the y underscore predict. So you can even check with the accuracy score. A scalar matrix, right, that is present in the accuracy score. Import. Yes, if I know the accuracy score, just you can just yeah, give this predicted and actual values. It gives the score for us. Even manually we can evaluate as well how many correctly classified divided by the total number of predictions. Wait, predict. I think this is the capital one. Yeah, it's now 100% accurate, my system, right? Only few models are there, and then it is perform well. So even if you want to check with the confusion matrix, take the confusion matrix as well. Same accuracy score in place of accuracy score. I can use the confusion matrix. Yes, that's all. So that's all. So out of 5 correctly classified as the 5 uh, out of 5 correctly classified as the 5 flatware sorting. Out of 3 water tap running, 3 are correctly classified. All the 8 samples are correctly classified just using a simple logistic regression and 40 audio samples. So any doubts in this?
Participants.
Yeah, any doubts? So just from the beginning, from the scratch, so just how to create a feature matrix and many more things are there, but still time is the constraint. Yeah, any doubts on this point?
I think we don't have any doubts, sir.
Yeah, okay.
Thank you, sir. Thank you for a wonderful session. You have given us very good insights into how the working of these procedures. And for all the three sessions that you have delivered to us, thank you very much.
Thank you, ma'am. Thank you so much, ma'am. Thank you.